Thanks everyone for joining this talk. And before actually starting, I would like to share the motivation actually of giving this talk. So we've attended the last year RabbitMQ Summit, not me personally, but my team members. And then we generally have a knowledge sharing session within our team around what was the knowledge gained from the summit and what kind of things that we could include in our normal day-to-day work. And towards the end of the debriefing session, we asked ourselves actually, what would have been a topic that we could have contributed into or was missing last year? And we came to the conclusion 1 year ago that monitoring was not really covered in the first summit edition. So we were set from 1 year ago, we're gonna come this year and present this topic and how we're doing this. And here we are today. And actually it seems like we were not the only team that thought about this. So monitoring seems to be a first-class citizen in 3.8, like with native Prometheus support, and at the same time a Grafana plugin that gives you all the dashboards that you could need. And other talks today as well are focusing on monitoring or tracing on how you get better visibility over your system and how you run it. And this is basically what I'm going to be talking about, how we monitor our system in its production state nowadays. Unfortunately, we're not yet at 3.8, so all of my talk is covering around what we use to monitor from 3.6 onwards, and our experience based on what we were monitoring at that point in time. So that's an overview of what I'm going to be talking about today. So an intro to Zalando, an intro to our team actually, and what we're doing, and how we use RabbitMQ. So basically we use it in our own product. And what we do monitor today, and what does our monitoring look like, what we have learned, so a couple of information like from the trenches, what we have observed monitoring our system, and then how we actually use RabbitMQ telemetry to scale our system dynamically. So that's Zalando basically at a glance. So we started off 11 years ago, but nowadays we operate in 17 countries. We have a little bit over 29 million active customers, so people who perceive Zalando as the starting point of fashion, so we seem to be on the right track. Most of our traffic actually comes from mobile devices, so whether that's mobile web or our native apps. And this slide actually was just updated the day before yesterday because I had October numbers, but we shared our November numbers. So we have, in the past quarter, more than 1 billion site visits. And in total, we're like 15,500 employees, and a headquarter in Berlin with around 3,000 engineers focusing on different engineering problems around the fashion space. And this is actually customer inbox at a glance. So has anyone shopped at Zalando before? So probably you've interacted with our product. So customer inbox is the team that manages the inbox premises of the customer. So we view your email inbox as a premise and as a window actually to our shop as well, coming back or getting the information that you need at a glance. At the same space, actually, your notification center is an inbox from our point of view as well. So this is a spot where we're able to reach our customers and notify them about the information that they care about. And customer inbox is mainly the team that builds the overall tooling around communication with our consumers. So we have an in-house built tooling around template designing, audience building, campaign setup, and sending transactional and commercial communication to our customers. And we always strive actually, while we send the communication to the outside world, to our customers, that it's first of all supportive, so it provides the needed information that a customer needs at that point in hand. So whether that's creating an account, getting a confirmation that your account has been created, signing up for our newsletters and knowing more through our newsletters, or in the transactional flow where you get your order confirmation, shipping confirmation, return confirmation, payment, open invoice, all of this transactional flow that gives you the right piece of information at the right time, and at the same time is very supportive around what you need to do now. On the other hand, we want to build a very deep relationship with our customers. So we don't want our communication to be only transactional. We want also our commercial communication with our customers to build a long-lasting relationship, that they find the message that we send come to them at the right point in time, whether that's at the moment when they're waiting for a sale or at the moment when they've bought something and they want to couple this with something else. And this is what we mainly focus on customer inbox side. We're not only supporting just emails and push notifications, but those are our most prominent channels that we use. But we also support sending SMSs and Facebook Messenger, and this is the whole premise of building our platform in-house, that we can easily extend this towards any channel in the future. And that extensibility comes with the fact actually that we rely on Rabbit as well, because at any point in time, you could just have another topic, another routing key, another consumer, and out of the box you have another channel. What next takes me actually to the pillar point of what we've done with the solution. Has anyone been just woken up at night to just add a couple of more instances? Not as much as people in my team would see, actually. We have seen this a lot. So within customer inbox, we are 4 multidisciplinary teams working on the same product. So in the end, we have the product that builds the audience and at the same time builds the template and also sends this out to our providers and collect the asynchronous and synchronous feedback about what's going on. And this whole product is supported by a 24/7 round, which is generally the majority of the 4 teams participate in our 24 rounds. And we normally have what we call a warm meeting, which is the weekly operational review meeting that takes place with the handover of the on-call duty between one person to the other. And then that's a 1-hour meeting where we go through our SLOs, product SLOs alongside specific service SLOs, and also going through the incidents that occurred. Why was this person woken up? What was written in the post-mortem? What kind of action items that were there? And we've noticed a pattern that sometimes we're just woken up at night for someone to just add a couple of more instances. Messages in the queue are just drained, and afterwards scaling down the application. Everything is working fine. It's sort of anemic post-mortem at that point in time. What was the action item, and gained knowledge out of this is that probably we're having more messages than expected, and we just would have scaled. If we would have scaled on our own, that would have solved the problem. And this is actually what we've been able to do over the past year in 80% of the cases, because generally just scaling sometimes might worsen the problem that you have. So you just need to be careful around what kind of applications that you're able to scale dynamically without caring for this. So you just need to make sure that you don't end up in another bigger problem where you're scaling an application where you don't have the available connections to a data store, or you're scaling an application that has a dependency on an upstream system where you're actually causing more harm in the customer experience than benefit by protecting your own system. Because if our system scales and we're able to handle messages at a higher throughput, that doesn't necessarily mean that the customer would enjoy this, because if the shop itself is not able to scale as fast as we can, customers will not be able to interact with this. So we're just 80% is the amount of time and is the amount of times that we've observed that that's within our domain, and scaling made sense. But before talking about how we scale, I'd like to give you an intro about our setup actually, and how we use RabbitMQ and what other things that we actually rely on. So RabbitMQ is the inter-product broker within the customer inbox realm. So within Zalando in general, we have another event streaming platform, which is called Nakadi. It's an open source project. And this is where most of products communicate when the messages between systems are relevant for other products as well. And this is where we generally get information about other things that are happening outside our realm. And then we process everything that's within our domain, within our RabbitMQ cluster. And that is split into a constellation of group products, like when we build the audience of customers that we want to actually communicate to, or when we're just consuming events that happen on the platform in general and start communication with the customers right away, and building the message and sending it out. We're generally running on a 3-node cluster with a Dockerized RabbitMQ running on AWS. And that's the actual official logo of an EC2 instance, by the way. That was a new learning for me while creating those slides. And in general, like those 3 building blocks are a constellation of 70 microservices that deal with everything around message building, template building, asynchronous and synchronous feedback. And not all of those are connected to the RabbitMQ broker, so I think around 22 of those actually have direct connection to Rabbit, but the whole platform interconnects and work together. And within our setup, actually, we rely on different feature sets that are provided by RabbitMQ. So we have high availability queues for everything that's within the hot path of a message that we want to make sure that it's highly available and running on different instances in case that we miss out on a node while operating. We rely on publish confirms as well for messages that we want to make sure that we shouldn't lose, so that they're always sent out. So in that case, for instance, a password reset or an order confirmation, we don't want to miss out on sending this email out. Like, this is something that a customer expects. Most of the cases it's legally binding as well, and you don't want to miss out on sending on an order confirmation. We rely on a couple of exclusive queues as well, and this is something that I'm going to get into of actually why we use them and how we're using them. We have a couple of lazy queues that's mainly around dead lettering or delayed processing while bundling certain things together. And that's basically our setup at the time being. We have a blue-green deployment with a predefined configuration file, so that's something that was mentioned earlier in another talk, that it's better to have your topology in a centralized place so that you're able to just deploy another broker right away. So this is the case for all of our exchanges, binding, and queues that we know that we need them. On the other hand, we have a couple of queues and exchanges that are dynamically created by applications based on interactions with our email management campaigning UI, which the application takes over by itself actually when we deploy from one broker to the other. And how we're collecting metrics. So we rely heavily actually on the management endpoint plugin, so that's enabled on our cluster, and we poll actually the management API endpoint to get all of the information that we store. And we do this with a tooling called Zmon. So that's actually a Zalando open source monitoring and alerting tooling that has kickstarted actually as a Hack Week project maybe like 5 years ago because of the lack of the possibility within normal monitoring tooling to define any entity that you're interested in. And that was one way of dealing with this. And it's a very flexible solution of defining any kind of entity that you need, create checks. After creating a check, creating an alert, sometimes just a dummy alert as well, that you make sure that the check is periodically running and you're collecting all the data. And the data is persisted for, by default, 30 days. And then you hook this up to Grafana so you have nice dashboards of visualizing everything. And since I mentioned on-call duty, we rely on Ops Genie actually as well for getting paged. And this is directly hooked up to any of our checks in Zmon that we consider mission critical. So by default, we have tier definitions of application and what is an application criticality within the whole Zalando realm. And a critical application by default comes with a critical alert that comes by default with a critical team that takes care of the on-call duty of all of this. One thing actually that I would like to mention as well, while polling the management endpoint, we generally do this on the nodes aggregate endpoint to get all of the information of all nodes, because we run on a 3-node setup and we aggregate this information in, so you get aggregate informations and individual information from nodes. But if you're running a multi-cluster setup, your monitoring system is ideally aware of what your nodes are, so that it could automatically poll each and every node on its own. Or you might have a different setup where you have a dedicated node that runs for monitoring and reporting to aggregate everything. That would be something that your check system needs to be aware of while polling this. Another thing actually, that this is something that you shouldn't be doing very aggressively. So just running a check every 1 second might not be that beneficial, because the management endpoint at the moment is highly coupled as well with the runtime of the Rabbit itself. So while excessively polling it, you might actually cause more harm than visibility. So our checks are generally running at a 30 to a 60-second interval, and that's generally sufficient in our case to have the visibility that we need over our cluster at that point in time. And That's a snippet actually of our Grafana dashboard. So most of the dashboards are our own opinion of what we actually monitor. That does not mean that that contains all information that you could actually monitor. The endpoints are very excessive and verbose. Actually, the information that you could get everything that you see in the management UI alongside a lot of things that you could combine this with your own application stack or clients together. But most of the screenshots that I'm showing now are actually just from our RabbitMQ Grafana dashboard, but this is not the only dashboard that we use to monitor. So every application has generally its own dashboard where it monitors its own performance, data stores, and everything, alongside its own connections and channels and published consumption rate from Rabbit. But that's just from our Grafana dashboard of RabbitMQ, which is generally a very good starting point for me to check up where is things going wrong, if something is going wrong, because that gives you a very high visibility on the overall broker. And the first panel that we have is actually about the infrastructure system itself, and we split our monitoring very similar to how it is documented as well within the RabbitMQ monitoring guidelines. So we monitor the system, the underlying system itself, and the Rabbit nodes. We monitor the queues, the exchanges, the overall footprint of every queue and exchange, and number of messages and messages in RAM and all of this, alongside the clients. And this is how the panels are set. And the first overview here is actually from the nodes at a glance, which are our 3 nodes. And this is where we monitor the I/O rates, the operations, the available disk space, the used memory, the file descriptors. Whenever actually you see a bump over here that goes beyond your limit, that's an alarming thing to look at, because this is where Rabbit would probably start throttling your producers alongside your consumers not being able to catch up. The instance of the memory usage and where it is from the watermark definition of our broker as well. So how far we are and how far we have leeway. And the CPU usage of all nodes. And then our next panel that we actually have as well on the very big top is actually globals. What's happening on a global level over there. And we monitor the global queue statistics, so the overall number of messages, and the overall number of messages that are in a ready state, and the overall number of messages that are in a rejected state, or have been rejected by a consumer, alongside the messages rates themselves. So on a global level, and the overall number of connections and the overall number of consumers that we have at any point in time. That's highly fluctuating depending on how many instances we run for every service, but they all should be slightly in line. So if you see an uptick in message rate, while at the same time our consumers are unable to handle this uptick, we would see also an uptick in the number of connections and consumers automatically scaling out to deal with the throughput. So if you look at a bigger time frame, you would see this scaling up and down rapidly very nicely. One thing to point out over here actually, so the number of consumers that we have on this panel is almost 10,000, but at the same time there is around 2,000 messages that are not being consumed. But actually the number 2,000 has something in our system, so we generally have dead letters, and a couple of messages might be dead lettered, and we have alarming and alerting on different thresholds that we have. And for commercial messaging, dead lettering 2,000 messages actually is within our acceptable SLO while we send out commercial messages. So this is something that we just have in our dead letter queue. We're not consuming, but if it increases beyond this, someone will probably get an alert and have to check on this. Then we have an overall panel around the queues. So actually the message rate per queue, the consumer utilization of every consumer, and the number of messages per queue, the actual RAM usage per queue. So what is actually those, because we have different sizes of different messages. So an entry message coming into our system before rendering or templating or figuring out what's going to be eventually going out is very slim. On the contrary, a message that's already rendered and it's just an email that's about to go out. So a small number of messages in that queue might have a very higher memory and CPU footprint than a small message in an asynchronous feedback queue that we use to persist information about the metadata of the message itself. So we look at this hand to hand alongside the message bytes per queue and the message byte in RAM as well per queue. So that gives you an overview of how many messages you have, actually what is the message rate per queue, and what is the footprint that you have per this queue. And that's a very good view actually of the consumer utilization. So this is generally how consumers should look like at 100%. 100% means that you're utilizing your system at its best. Your consumers are able to cope with the production throughput of your producers. You don't really need to add more consumers at any queue. And everything is probably in memory, which is the state that we always try to strive for. But in reality, that's not always the case. This is actually a view from a busy time of our queues at a glance. So if you actually look in between, that was almost around midnight, where we're generally not sending anything to our customers post 12, 1 a.m., because this is generally where most of the people are sleeping, and we generally try to optimize to open rate. So we try to send early in the morning. But then if you look at this at an earlier point in time in the morning, we have a lot of consumers actually being underutilized and then popping back up. And at the same time, we have a higher message rate per queue. So in general, most of our queues at around 1,000 operations per second. And we have some backlogs in certain queues. So some queues have 20K messages that they still need to start consuming. In general, not having 100% consumption utilization, it's not the perfect state, but it doesn't mean that your system is not functioning, because a consumer can slowly lag, but then all of a sudden it can start picking up again. That's whether the producer started slowing down on production rate or the consumer application started adding more instances. So 100% is the optimal that you should try to optimize for. Being below 100% for a very long time is something alarming that you should start checking your application code, why your application is not catching up actually with the production rate. But having smaller dips and then catching up again, that's generally how you see your system dealing with burstiness of certain producers, where a producer all of a sudden wakes up, produces like 1 million messages, and then all of a sudden the consumers are just prefetching, sifting through messages and starting processing them slowly but surely. Then, to give you a little bit of an overview of our application stack before driving into clients. So most of our backend services are Java Spring Boot applications, where most of the applications that running at Spring Boot 2.0 or higher have Prometheus by default. So this is where they report everything to centralized checks of the application state. Alongside anything that's still running below Spring 2.0 is actually reporting all of this to the normal health check endpoint, where we have an overview of all the interaction of this application with our broker. So we generally report number of consumers, number of connections, number of channels, publish rate, consumption rate, and each application has its own user as well, so we have this overview per application. So generally that's a very easy way for us to know like which application at the moment is hogging on more resources and which application is producing more than consuming. The majority of our applications actually are either producers or consumers, but we have an overlap set of applications where they both produce and consume, where I would generally recommend that you run the production and consumption on different connections with their own channels, because that will give you better throughput in general, and that would not impact your application if the consumption is throttled while the application publishing is not throttled at all by the Rabbit. And as always, the more you monitor your system, the more that you get to know about it, or the more the bad things happen actually, the more you get to know actually what's going on. So a very interesting learning form for me personally within our organization is our 24/7 chat, because this is generally where someone gets pulled in and then someone actually shares a tracing overview or a Grafana dashboard or a check that goes flaky, and just going through this monitoring pieces of the organization that generally gives you a more holistic overview of what's actually going on. And this is by practice what we figured out as well within our system. And I would like to share with you a couple of more examples of what we learned while we monitor and the use case of the thing that we learned. So as I mentioned earlier, actually we rely on exclusive queues. To give you a little bit of more context around how we do this and why we do exclusive queues, the most computationally intensive process in our pipeline is actually rendering the message itself. So we've built a templating solution in-house with our own UI where marketeers can go inside the tool, drag and drop any base components that they want to fill in a template, and then that automatically generates the template that could go out. It could be either a push notification, an email, or anything else. Email is generally the most intensive because we have to render the full HTML at the same time we render the actual text content, and then we have to render both, and we have a rendering system that renders all of this. And microservice architecture, so like every service is in a bounded context, so templates are in a system, rendering happens in another system, and there is an orchestrator in between. So we have, as most systems do, a worker service that knows about the message, fetches the template, then calls the rendering system, renders the template, and then passes this on into another exchange and queues to go to the different senders. And we started caching actually the actual template state in the rendering engine of what template that I'm rendering at the moment. And we had a distributed cache, so we relied on Redis. But that was not actually cutting it through to the SLO measures that we had in place, because generally we define the SLO of the product, and then that's something that we don't break. And afterwards that moves further, but with different workloads, we have to optimize further to meet all of this. And we ended up actually with local caching as well on the render services themselves. But those are services that actually scale out on their own. So this is where we relied actually on Spring Cloud Bus alongside exclusive queues. So our template service generally publishes a template change event inside our RabbitMQ for coordination between both template service and render service. And within the render service, the first instance that picks up the message fans this out through the Rabbit Spring Cloud Bus to n number of render service instances to invalidate their local caches. But the render services themselves actually dynamically scale, either based on queue backlog or based on CPU. And you cannot really check on the number of exclusive queues that you plan on monitoring if this number actually always changes, because you just scale out, scale in, and then yeah, you have queues, they're there, but you need to know the actual numbers that you need to check against. And this is what Zedmon, alongside the management endpoint, helped us do to have clear visibility over all of this, because with an AWS instance that runs an application of ourselves that's defined as an entity, and we know how many entities running actually for this application. At the same time, from the management endpoint, we know how many exclusive queues are running at that point. And once an application passes the health check and becomes hooked up to the load balancer and actually it starts getting traffic, we know that it exists, and we know that it has a binding exclusive queue along next to it. And if those number matches, then everything is fine, everyone is connected, everyone gets invalidated in the right manner. If we have a mismatch between those numbers, actually, then we have an instance missing a queue, which we then have to either intervene or replace, generally just killing the connection, which is something that we do automatically as well. Solves this issue. But this was our usage of exclusive queues, and that was the learning actually that we've gained around monitoring the number of exclusive queues, around the number of instances running, and how to actually have better visibility around the usage of exclusive queues and what you expect from them. Another learning actually that we know is the defaults of number of cache channels. So a little bit of context as well around channels. So RabbitMQ generally have a long-lasting TCP connection from the application to the broker itself. And then within every connection, you actually could multiplex this to multiple channels, and that gives you either a higher throughput while publishing or a higher throughput while consuming. And It's generally recommended that you have a single channel, single connection, and utilize multiple channels within your application. And while we were monitoring our applications and our channel churn rate, and we've noticed actually that we're not optimizing the channels creations in one of our applications to the expected throughput from this application. So we dug deeper. So we figured out actually that the default of the caching connection factory in Spring Boot is actually one cache channel. And once our application introduced publish confirms, because it was an application that produces messages that we wanted not to lose at all, and while the application starts opening a channel, starts publishing into it, awaiting acknowledgement, it started creating way more channels than we expected. And we have been able to drill down the root cause of this because we were not reusing channels at all. We were starting up a channel, the number of cache channels that we could use is 1. So there is only one channel cached, another thread picks it up, but we have 200 threads running in parallel, so all of those try to create channels. One of them finishes, caches one channel, picks up by the next thread, but the other threads that are currently working are also generating other channels. And that was very evident in our graph. Like we saw like 2,000 channels by a single application and like a huge memory footprint because you get channels are relatively cheap towards connections, but they're also using resources, and you don't want to waste your resources on something that you could optimize. So what's recommended generally is having like a single-digit number of cache channels, but we actually went a little bit higher because the application in place that we're talking about is actually consuming from our event streaming platform, where we might have actually a backlog of 10 million messages, and we want to actually, and those 10 million messages are 10 million price reductions that happen overnight. And since we don't send communication overnight, we start in the morning, but we want to go through the whole backlog before the peak normal transactional flow of the shop and people ordering. So we want to finish up knowing about price reductions, matching all of this with customers that are interested in items that are now reduced. So we capped the number of channels actually to 200, which gave us the right amount of throughput that we need with the right configurations of threads that are running in this application, with the right number of batch consumption from our external event processing platform. So that gave us the sweet spot. And you're able to actually cap this using the connection factory by setting a timeout. So if you set a default to the number of channels without a timeout, you don't really actually cap this. But if you set a timeout, then you actually reach a cached number of channels at the same time a capping of those channels. So that was our next learning. And the other thing actually that we did, it's another usage of the management endpoint that we use actually for flow control, sort of parking and processing messages in an exponential back-off manner. So as I mentioned earlier, we rely on RabbitMQ as an inter-product broker, but at the same time within the company we have an event streaming platform. And coming to the price reduction use case, for instance, so we have a constellation of services that's aware most of the time of what's on your wish list or what's on your cart. And then whenever there is a price reduction happening on the platform, we try to match those reductions with customers that are interested in this. So that's the audience building part. And then that triggers events that go into outside of our Rabbit system towards our event streaming platform, which we then consume again inside our Rabbit system for enrichment, and then we process the message. But since we don't have commercial communication running at night, we generally park all of this on our event streaming platform. So we don't want to actually park those messages inside the broker because we would like to optimize the usage of the broker actually to always have everything in memory. And our event streaming platform is built on top of Kafka and is built actually for different teams to consume based on whichever cursor that they're in. And it provides the functionality of parking messages outside. So this is what we do. And then when we wake up in the morning, our set of services, and then they start processing, we actually check the number of messages inside our RabbitMQ for a specific set of queues. And if we still have messages over there, we actually throttle our consuming application that brings messages in until our services inside have processed this backlog. So that's another interesting usage of telemetry within a production workload. But I would highly encourage that you use this with a lot of caution and having same defaults on your end. So within our application, it's built in a sense that the management endpoint might not provide a value, or we have a same default, and then based on this we decide whether we want to throttle or not, because that mixes also your production load with telemetry information. In our case, it made sense because we had a default that we could fall back to, and it made sense in our normal processing pipeline. But that was another interesting usage of the management endpoint to back pressure processing and parking messages outside of our broker so that we make sure that our broker is performing in line with our expected throughput and SLOs. Now that takes interesting branding. I know the color matches the RabbitMQ color. That was not intentional actually. That's the light version of AWS branding for CloudWatch alarms and Autoscaling. But an interesting coincidence. But what we've built actually around the telemetry and management endpoint is a Lambda function. So as I mentioned earlier, we run on AWS, and over there we've built a small Python Lambda function that actually polls the management endpoint and fetches the queue sizes of queues that we're interested in, or also sometimes does a computation of a combination of queues that we're interested in a single metric. And then the Lambda function reports this information to CloudWatch, and based on the metrics that we set in CloudWatch, actually we define CloudWatch alarms to actually trigger our auto-scaling strategy. So within a combination of services that we have the primarily scaling strategy now is based on queue backlog. And you could set this based on the queue having an absolute or a relative value more than X for X amount of minutes that would trigger the alarm. Based on this alarm, your auto-scaling kicks in. And then afterwards, if that does not exist anymore, your downscaling kicks in, depending on how you downscale and how you cool down. And this is how we solved actually scaling our consumers, where scaling of those consumers made sense automatically without letting anyone get woken up at 2 a.m. to just add a couple of more instances. And this is actually how it looks like in practice. So I think that was last week. I was checking our auto-scaling strategy, and when auto-scaling kicked in based on a queue backlog. And that's, I think, early in the morning. That was around 8. And the combination of both those queues are generally a good indicator on our end that we need to scale a further downstream dependency that will be overhauled with load. So as I mentioned in another example, like we have a worker where worker just delegates some calls with different services and then publishes a message outside. And one of those dependency actually scales based on queue, because that was a better indicator on our case than like request latency or CPU usage, because based on those messages on those queues, we already know that this service will start working now. So by taking those matrices in, reporting our scaling, at the time that the messages reach the service is already ready to deal with this workload. And you could see this in practice. So we were piling up a couple of messages over there. We were running at 4 instances at that point in time. This service actually scaled to 6 because that's our increment step. We add 2 more instances at a time. And then once the backlog was processed, the service gradually scaled down. So in the end, from our point of view, we scaled in a cost-efficient manner. Like that's around 20 minutes to handle the burst of a backlog actually at a very fast processing speed. And this is actually not the only way to solve it as well. So there is actually a RabbitMQ plugin, not in the RabbitMQ Git repository, but it's actually an open source plugin developed by an individual contributor actually, and it's called CloudWatch Exporter, and it exports actually all of the information in the management API endpoint to CloudWatch. So if you want to try out what I just mentioned today, you could just enable this plugin and just export everything, but also do this with caution, because you're exporting all information, and CloudWatch bills you actually by metric that you export, times the number of nodes that you have, depends on your cluster setup, times the number of times that you actually export all of this, and it's tier based. And you pay more for the first couple of tiers, and you actually still pay more for the first couple of tiers if you move to another tier. And generally, that was one of the main reasons why we didn't opt in for using this. Another reason actually is that our Lambda function setup was in production 7 months before that plugin actually came into the open source community. But after it came out, we debated internally within our team whether we want to switch to this, deprecate our Lambda function or not. But in the end, we did basic math around how much we would be paying extra for CloudWatch, while anyway we have our own check alerting storage of matrix in our own in-house tooling, so it didn't really make sense to do all of this. And we thought about actually contributing into filtering out matrix so that it becomes a little bit more similar to what we have in our Lambda function. But also, we put this on the side because we're not going to use this plugin, because our biggest rock at hand that we want to solve is actually moving to Kubernetes. And at that point in time, that might pose other challenge of how we report those metrics. It might be done differently. We might handle this in our own controller that operates our cluster. So we're still debating this, but if you want to use what I've just presented just right away, you could just enable this plugin in your test setup, start seeing matrices over there. What also the plugin lacks is the combination of combining multiple matrix together, but that's actually a feature available in CloudWatch itself. So you could combine two matrix, merge them together, you get another matrix, and then based on the combination matrix, you could actually scale. But you have to do this with care as well, because if it's number of messages, that's easy. You don't really need to care about a lot of math. But if you're combining CPU utilization with consumption rate, then you have to be very aware of what you're combining together. And last thing actually that I want to share from our setup is across service boundaries and tracing and what we have been doing recently. So 1 year ago, we decided on adopting open tracing as an organization. So the magnitude of services that we're running in production with different production load is becoming unmanageable from a bird's eye viewpoint, actually, to get an overview of the overall architecture, different dependencies between microservices and systems. So within our team alone, which is like a 4 multidisciplinary team, we run 70 services. Zalando has 200 teams. We run almost 6,000 microservices in production, and getting a full overview of like a business transaction or a production boundary without tracing becomes a little bit hard. So we've adopted open tracing, and we've set on Lightstep as one of our means to visualize our traces. And we also utilize the Lightstep plugin in Grafana as well to oversee what's going on. And what this has been beneficial in our case when it comes to communication and different communication workload is that we've defined the streams of a trade, which is a collection of spans and traces that intercept multiple services based on the business function that we care of. So generally there is a stream running on order placement. That doesn't just include our system, but that includes checkout completed, order placed, payment pre-authorization occurred, like reservations on stock level occurred, order position level reservations occurred, and data or a business event was emitted to the event stream bus, our system consumed it, then we started emitting into our Rabbit cluster, and that gives you a very holistic view of what's going on. So how we did this within our team is that we built a small client library for tracing actually everything going inside Rabbit. So with an annotation so that it's not that intrusive within our code base. So you just annotate when you're publishing or consuming, and then by default that starts shipping the traces. And we have within each service and our product overview Grafana dashboard, an overview of our RabbitMQ performance within the context of what we want to serve as a business. So when it comes to order confirmation, we have an overview of whether our production or consumption is generally breaching the SLO that we've defined for this exact use case. So not just looking at RabbitMQ holistically or at a queue or an exchange or a service, publish or consumption rate, because our system that consumes and enriches data does this for like 200 events. But in order to have the visibility on a specific use case that you're interested in, we figured out that relying on tracing and seeing all of this in our Grafana dashboard made more sense. And we're able to see actually that we're meeting what we committed on as a team or as a product. And that's the last thing actually that I wanted to share with you. I would recommend it. Like, it's not in production for a very long time. Like, we've instrumented our services a year ago, but now it's actually starting to pay off because all other teams instrumented their systems. So if you check a span and a trace now, you could see what's going on throughout the whole organization. Thank you.
Thank you. So, do we have any questions from the audience?
You mentioned you use Autoscaling for your consuming applications. Do you also use it for your RabbitMQ clusters?
For what?
For the RabbitMQ nodes in your clusters as well.
So the question is, we use autoscaling actually for our consumer applications and whether we're using this for the cluster itself. At the moment, we just have a single autoscaling policy actually to maintain the 3 nodes that we have on 3 different availability zones, but we're not scaling the cluster itself. So we don't, like, not based on publishing or consumption, add another node. But this enables us, if we lose a node, that we can easily replace this node. So this is our reliance on the autoscaling strategy so far, which might get interesting when we move to Kubernetes, because as I mentioned, that's our next big rock that we have on our side, because Zalando declared Kubernetes as the native runtime environment. Half of the architecture at the moment in the company is running on Kubernetes, and we are next, so our team needs to move. But that would be an interesting thing to solve. If anyone has solved it already, like, just raise your hand. I'm going to pick your brain a little bit. If someone shares our struggle as well, then we should combine our forces and find a solution for this.
Any more questions? Well then, thank you so much. And now we're ready for lunch. So we meet you back here after lunch.